Okay, so what we have? We have a function u. It is defined in a D subset of Rn. It has values in R. Okay, and we want to find maxima and minima of u in D. Okay. Now we assume that D has a non-empty interior. Okay, so we assume that the interior is different from the empty set. Okay, we will do also more assumptions about D in next parts of our discussion. Why? Because we are aware of the fact that different sufficient and necessary conditions are possible for maxima and minima depending on the following fact. Is the maximum in the interior of your domain, or is this maximum or minimum on the boundary of the domain? You are aware of this. So I remind you that if you have a function defined in an interval having real values, it could be that here you have a maximum, local one, but the absolute maximum is here, and you know that here the derivative is not 0. Okay, so if you have a maximum or a minimum in the interior of your domain, you find that a maximum, if a point is a maximum or a minimum, then this point is such that the derivative is 0. Okay? While if on the other side, if you have that your function attains a maximum or a minimum on the boundary, then it could be that the function has not a vanishing derivative there. Okay? So we know that different conditions, different necessary and sufficient conditions are to be found depending on the point of maximum and minimum, let us say the localization of this point in the interior or on the boundary of the domain. Okay? So, I repeat, we already know that for functions defined in an interval, the derivative is vanishing in maxima and minima localized in the interior of the interval. And we already know that different conditions must be conceived if you are on the boundary of the domain. Okay? Okay, now you know, this is a result which you should already know. It is classical standard mathematical analysis. My generation studied it in the second year course in mathematical analysis. I don't know what they have done now with the changes of the curricula. If you have x0 belonging to the interior of D, and if x0 is a point of minimum or maximum for U, okay, so these are the hypotheses, and if U belongs to C1 D0, okay, so if U is a continuous with its and all its partial derivatives are continuous, so with all these assumptions we can prove that grad U calculated in x0 is equal to 0. Okay, and this can be proven with standard arguments based on Lagrange role theorems. Okay, but if you want to remember the reason for which this result is true, think always to a Taylor expansion. I mean, this is for proving this theorem with the Taylor expansion representation of a function. You need more assumptions than those strictly necessary for proving the theorem. Okay, actually this theorem is based on Rolle-Lagrange theorem, which tells you that given a function which has this value and that value in A and B, and if it is sufficiently regular, C1 in this interval, then you have one point, at least one point, such that the slope of the tangent curve is exactly equal to the tangent straight line is exactly equal to the angular coefficient of the line which is connecting the point A, FA, and B, FB. Okay, so this is a standard theorem in mathematical analysis. Okay, the idea which must drive you and which will drive us in generalizing this result is the following. If I have ux equal to ux0 plus grad u x0 x minus x0, here you have an inner product, the standard one in Rn, plus a remainder, okay, if you have this representation, okay, remember always that the remainder here has a dominant term which is quadratic. Okay, so you can impose that this quadratic remainder has is definite positive or definite negative. Okay, so this term is always positive, for instance, if the remainder is definite positive. Okay? And you assume that ux minus ux0 is positive because x0 is a minimum. Okay? Now you are asking yourself, how can I find the gradient of u in x0 knowing that this is positive and this is positive in the neighborhood of in the neighborhood of x0. I repeat you, this is not the proof of the theorem. This is a way for reminding, this is the heuristic reasoning. I hope you know the meaning of the word heuristic. Okay. Eureka in Greek means I have found. Eurisko means is the verb I find. Heuristic is a reasoning which is developed for conjecturing the result. Then you need a rigorous proof. Okay? So the question is, this has to be positive in the neighborhood of x0. This is positive in the neighborhood of x0, and it is smaller than this in the neighborhood of x0. Okay? So now the question is, can grad u be different from 0? If I have a grad u, I take this x minus x0 and I get that the inner product is positive. I take minus x minus x0 and this inner product is negative. Now you understand why we need to make the assumption that x0 is in the interior of the domain. Because you need to move around x0, always being able to calculate the function u. Okay? So, if this quantity can be positive and negative, and as this can be bigger, is bigger than this, when you go close to x0, then this animal is dominant and can change the sign of this increment. So, if you have chosen x minus x0 positive, you believe you to be happy. You say, okay, positive, positive. The sum of two positive quantities is positive. But then you change the sign of x minus x0, and this becomes negative, and as this is a higher order infinitesimal, this term becomes dominant. So you have a contradiction with your assumption. Okay, so the fundamental idea of the theorem I am quoting here is this. It is not possible in a minimum or a maximum, which is in the interior of the domain, to have a non-vanishing gradient. So, if x0 is minimum or maximum for u, then the gradient of u must be 0. There are bad points in which the gradient is 0, but these points are neither maximum nor minimum. So being grad equal to 0 is not implying anything about x0, except that x0 can be candidate to be maximum or minimum. Okay? So this is a necessary condition. Okay? To be maximum or minimum. But it is not sufficient. Okay, so this condition is not sufficient to this. Okay? Okay, so this is what you should already know and what we assume that you already know. Okay? Now, what we want to study? We want to study maxima and minima of u in a domain D, which is not an open set in Rn. So let us go back to our definition of constraint which we have given in the last lecture. So we said that Lagrange wanted to study the problem of finding the maximum and minimum of a function in a domain D, which is defined as follows. D is equal to the set of x belonging to Rn, such that fi of x equal to 0, I equal to 1 to n. Okay? So we discussed yesterday that we do not want to define D as an open subset or a compact subset with non-empty interior in Rn. Giving some examples from economy, from mechanics, we understood that in general you do not want to maximize or minimize a function whenever you want. I mean, in domains which are generic subsets of Rn, we want to characterize in a specific way the subset where we are looking for maxima and minima. In reality, what happens is that we can prove theorems only for this class of subset. Okay, so we are developing mathematical models with the tools which we have. Okay? And we discussed that this set of functions must be such that the Jacobian matrix dfi over dxj, this is k. We have discussed the fact that k has to be greater or equal to 0. If it is 0, we recover the case we have already discussed, but this k has to be smaller than n, because we want a set of constraints which is smaller than the number of independent variables in Rn. Okay? And we said that we do not want to over-constrain our system, because otherwise it can happen that this set is empty. We imposed that this Jacobian matrix has a rank, so this is the Jacobian matrix, the rank of J is exactly K. So all gradients of Fi's, when used to form a set of vectors in every point of D, okay, they are an independent set of vectors. Okay? And I told you to be very careful. You should never believe that if I have n parameters, I write k equations, then I have left with n minus k independent parameters. I told you that if you have a sphere and a tangent plane to the sphere, you write two equations for a set of 3 independent parameters, and as a result you get only one solution, the point of tangent. Okay, so in that case 3 minus 2 is equal to 0. You have 3 degrees of freedom, 2 equations, and you are left with 0 degrees of freedom. Okay, so the request of non-singular Jacobian matrix is needed because of Dini theorem to be sure that when you impose these k equations, if you have x0 which verifies all these equations, in the neighborhood of x0 you can represent n minus k of the variables in x as a function, k of these as a functions of the n minus k. Okay? So you are left n minus k completely free, and the other k's are given as a solution of these equations. Okay? Okay. I don't know if you ever studied in your life the theory of embedded manifolds. A surface is a sphere is a surface embedded in R3. A cone is a surface embedded in R3. There are difficult problems when you are in the vertex of the cone, because this condition is not verified there. But in all the other points of the cone, you have a tangent plane. Okay, so this condition is verified. Actually, the domain D, which we are discussing now, is an n minus k dimensional manifold embedded in Rn. So this is the generalization of the concept of surface. It is an hypersurface, and every point in this hypersurface can be characterized by n minus k parameters. So a sphere is a two-dimensional surface in R3. A curve in space is a one-dimensional surface in R3. So you can imagine in R25 an embedded manifold having 11 dimensions. And Lagrange was actually starting with this definition the study of the theory of manifolds. Okay? But for our discussion, this is only suggestive. So you can think D as a kind of hypersurface in the space of n dimensions. Okay? Okay. Now, a particular kind of hypersurface is a curve. So if you can define gamma, a curve, in Rn, you have a parameter t which belongs to R, or even 0, 1, just for being specific. Okay? And this is a parametric representation of your curve. And you can consider C1 curves. So curves such that the derivative d gamma over dt exists everywhere. And d gamma over dt is the tangent vector to the curve. Okay? Now the trick which we will use now is to consider a point x0 which belongs to D. And a curve which is included in D and passing in x0. So imagine, of course we can only imagine surfaces in R3. Okay, so imagine a surface in R3, a sphere, and imagine a point in the sphere, and imagine a curve which is passing in this point. Okay? Why we need to consider these curves? So gamma of t, which belongs to D for every t. And we can also think that when t is equal to 1/2, gamma of 1/2 is equal to x0. So we have a curve which is included in D, and such that when the parameter t is 1/2 in the middle of your interval, the curve is passing in x0. Okay? Why we need this? We need this because we can consider the function u of gamma of t. We can consider the composed function. So we can consider a function which to every t associates u, which has to be calculated in n variables. Okay? Which n variables we consider? Gamma of t. So actually we have a real function of one real variable. Okay? So if x0 is a minimum in D for u, so let us assume that x0 on this hypersurface D is a minimum. Okay? What can we say about this gamma t function, this composed function? When t is equal to 1/2, this real function of real variable as a minimum. This is trivial, right? So, for every curve passing by x0, okay? We have that t equal 1/2 for this composed function is a minimum. Okay? We can calculate the derivative of this composed function, because this derivative has to be 0. So the total derivative of u of gamma t is equal to 0. Okay? We can calculate this derivative. Summation over I du over dxi gamma I dot, the derivative, okay, d gamma I over dt. Okay? So what we can tell, the gradient of u in x0, inner product, the tangent vector to gamma, is 0. So in a minimum point in D for the function u, the gradient of u is orthogonal to every tangent vector, to every curve which is passing in x0 belonging to D. Okay? So here you start understanding why Lagrange conceived the concept of tangent plane. And why in differential geometry the tangent plane to an embedded surface is defined as the set of all tangent vectors to every curve embedded in the manifold. If you want to imagine this with your geometrical intuition, you take a surface, a sphere, for instance. You consider a point of this sphere. Then you imagine all points which are passing in this, all curves which are passing through this point. And you imagine the set of all arrows which indicate, which are the representation of the tangent vector in that point. The set of all these points are forming the tangent, all these vectors are forming the tangent plane. Okay, so grad u calculated in x0, inner product the tangent vector t gamma is equal to 0. Now I erase this, I erase this, I erase this. For every gamma included in D, this condition is to be verified. Okay? Now, how is constituted the set T gamma? The set of all tangent vectors to every curve. Fi of gamma of T is equal to 0. You agree with this? Every curve gamma is included in D. So Fi of gamma of T has to be 0. This is the definition of D. Okay? So I can derive this function with respect to time. What I get? dFi over dxl d gamma L over dt is equal to 0. Summation over L. Okay? What it means? Grad Fi, inner product T gamma, is equal to 0. Okay, so what we have? Now you understand why we need the assumption of the Jacobian to be of rank k. Because now we must make a reasoning. Which reasoning we need? In every point of Rn, you can always find n independent vectors. In every point of Rn, you can always find n independent vectors which are pairwise orthogonal. Okay? So, how many grad f's you have? K. And they form a system of k independent vectors. How many vectors are orthogonal to these k grad f's? N minus k. So I have n minus k independent vectors which are tangent to curves embedded in D, included in D. So in every point of D, I find n minus k tangent vectors to D and k orthogonal vectors to tangent vectors. Okay? So the space can be split in the direct sum of k orthogonal vectors and n minus k tangent vectors. Why I'm stressing so strongly this? I announce you the bad news that this decomposition is not possible always in infinite dimensions. Okay? So it can be very painful to generalize this argument in infinite dimensions. Okay? But Lagrange had a genius in doing what is possible and avoiding problems. Okay, so he developed completely this argument in the finite dimensional case. Okay, so I have the vector grad u, which is orthogonal to every vector in the tangent plane of D. Okay? Which is the relationship between grad u and grad fi? Grad u is a linear combination of grad fi. Every vector grad u is a vector in a given point can be written as a linear combination of a basis. The basis which we have chosen is grad fi's and n minus k t tangent vectors. Okay. Grad fi inner product T gamma is 0 for every tangent vector. So grad u is equal summation over I of lambda I grad fi's. Lambda i's are called Lagrange multipliers. So I have proven carefully, slowly, that for every x0, minimum in D or maximum in D, when D is defined in this way, okay, there exists k Lagrange multipliers such that grad u is a linear combination of grad fi's. Okay? Now, you will see, I hope you will understand, playing with COMSOL, that modern mechanics could not be possible without this concept. We are talking about geometry. Geometry of embedded manifolds. Okay? However, this abstract concept is fundamental in designing buildings, for instance, or airplanes. It is very early, but I want to tell you, these lambdas are interpreted as vincular reactions. They are forces or couples which keep the constraint to be valid. So there is a beautiful interpretation of these coefficients. But it's very early. You will see this later. Okay. Now let's go ahead, because our story is not yet ended. So you understand, I hope that you understand that the theorem which tells us that grad f1, grad f2, grad fk can be completed with n minus k vectors to form an orthogonal basis in Rn. This theorem is based on Ruchet-Capelli theorem. Okay? You have the rank of a matrix which is exactly K, and you write equations for finding the other n minus k vectors, and this equation can be solved using Ruchet-Capelli theorem. Okay, actually these are the equations. T gammas are in the kernel of J. Okay, I hope that you are not fighting a battle against linear algebra. Okay, like your colleagues in engineering. So T gammas are the solutions, and you have exactly n minus k of the homogeneous system which I've written there. Okay? So this is clearly needed. And this is the crucial point, and the reason for which this argument cannot be easily generalized in infinite dimensions is exactly this. That not always in infinite dimensions this decomposition, the decomposition of the tangent space in two subspaces, one orthogonal and one tangent to the embedded manifold, can be obtained. Okay? Good. Now Lagrange remarks the following. Given U and given Fi's, I can write a Lagrangian L. Now this is a different Lagrangian, it's not the Lagrangian which we have discussed in the equation in minimization of action. Okay, you have U minus summation over I of lambda I Fi. The Lagrangian is a function of x and lambda. So here you have k lambdas and n x. Okay? The gradient of lambda, the gradient of L, is equal to grad u minus summation over I lambda I grad fi, the gradient with respect to x. Okay? So this condition is equivalent to impose that the gradient of L is 0. Not only, if I calculate dl over d lambda j, U is not depending on lambda. When I is different from j, the lambda I derivative with respect to lambda j is 0. When lambda is exactly equal to j, you have 1. So at the end of the story, this is equal to fj. So the trivial observation we can do now is the following. Now, Americans are very strange, and you understand that lambda is an unknown in this problem. Okay? Okay, I will go back to this. Americans are very strange. For some reasons, for forgetting everything we have done up to now, they write this with plus. Okay. Neapolitan tradition in mathematics and Soviet tradition in mathematics keeps considering the minus sign there in order to remind us the reasoning flow which was leading to this result. There is no reason you can use plus or minus. If you are particularly twisted, like some engineers, lambda 1 you place with plus, lambda 2 with minus, lambda 3 with plus. I mean, you can think everything. Actually, lambda is unknown. Also, minus lambda is unknown. Okay? By the way, I hope that you are not believing that minus lambda is a negative number. I mean, this is one of the big effects of the loss of mathematical knowledge in this generation. There are some students who raised their finger and said, so you assume that the minus lambda is always negative. Minus 5 is known to be positive. Okay, so this is a simple mnemonic trick for remembering the fact that grad u is a linear combination of grad fi's. Okay? But what we discover is, so grad lambda Lagrangian is equal f. So what we discover is, if x0 is minimum or maximum in D, then grad with respect to all variables, grad L is equal to 0. So before you had a n variable function u. Okay, and you wanted to find the constrained minima or maxima in the subset D, and the subset D is defined in this way. Is the set of all elements of Rn such that all Fi's are vanishing. Okay, and we have discussed that with the condition of Jacobian of this set of equations having maximum rank, we have discussed that this describes what we want to call an embedded manifold in Rn. And the dimension of the embedded manifold is exactly n minus k. Why? Because Dini theorem, implicit function theorem, tells you that if you have k equations in n unknowns, given n minus k of this unknown, not every, you must find the columns which are linearly independent, given n minus k, you can write the other k's as a functions of the independent ones. So this is an n minus k manifold embedded in Rn. Think, I repeat you, think always to the sphere. The equation of the sphere is x squared plus y squared minus r squared equals 0. Locally, in every point of this sphere, you can represent either x as a function of y or y as a function of x. You cannot represent always x as a function of y or vice versa. But locally, one of the two can be represented in terms of the other. Okay? Okay. So I want to maximize U on this embedded manifold. You can learn by heart without asking you why, and many people are learning it by heart, the trick. I built a Lagrangian. Okay? This Lagrangian is the difference U, the function which I want to optimize, minus the summation over I of lambda I Fi's. This is clearly a function of n plus k variables. So you are increasing the number of independent variables. The theorem which I have proven tells you that if x0 is a minimum or maximum, then grad L is 0. Now, we have written this condition. It is Fix equals 0 and grad U equal summation over I lambda I grad Fi. So what is telling you this? Find an x in D such that the grad U is parallel to, belongs to the orthogonal space to D. So the variation of U can be different from 0, but it has to be orthogonal to the embedded manifold where you're looking for a minimum. So U experiences a maximum or a minimum inside D. Okay? Now we count. We have how many unknowns? X0 and lambdas. And we have exactly n plus k equation. This is a good news. The bad news is that these equations are nonlinear. So we can have a lot of troubles in finding its solutions. The PhD thesis, the equivalent of a PhD thesis by Gabriel Piola, was the application of this method for solving many mechanical problems. Now, I tell you vaguely the idea. I will try to give you some examples. However, what happened is that what was really important is that modern numerical techniques for solving minima or maxima problems are based on the method of Lagrange multipliers. So when you will experience playing with COMSOL, how the software gives you some solutions, I think it is essential that you understand what is the method of Lagrange multipliers. Okay, so I will give you later some homeworks, I mean simple exercises you should do for understanding better this method. But now I want to go ahead and come back to our minimization problem. I needed this parenthesis. I will tell you immediately why, but in detail, but you understand. We said, given a deformable body, given its placement, I want to find the equilibrium solution for this body, the equilibrium configuration for this body, minimizing the deformation energy. Okay? So, I need an algorithm which produces for me an approximation of the searched solution. And you will understand immediately, I hope I have 1 hour, I must tell you in this hour why you need the method of Lagrange multipliers. Okay? So let's proceed in this. We said that we want to solve this problem. We block. Look, it is better if we do this way. I have the reference configuration C star, okay? Which is the shape of my body before any deformation process. Then I choose, are you familiar with this symbol? Boundary of C star. The boundary of C star, we assume it is a surface, and this surface is sufficiently regular for having a normal vector almost everywhere. Okay, it is existing except in a finite number of curves on the boundary. So you can have a cube, because on the edges of the cube you don't have a unique normal, you have two sides. So we choose dC star 1 and dC star 2. Okay? We choose two parts of the boundary of this volume, and we constrain these two surfaces to have prescribed placement. So if X belongs to dC star 1, the placement of x is given by K1 of x, and this is known, this is given function. And if x belongs to C star 2, Kx is equal to K2 of x. So I take this part of the boundary and I tell you stay here. And I take this other part and I tell you stay here. So I impose the placement of two parts of the boundary of this body. Okay? Then I ask myself, which K describes for me the equilibrium of this body when I have imposed these placements? In our last lecture we said, okay, I define for every point of my body a deformation density function. Energy deformation density function. So a function W, def, which depends on capital F and capital X. F is dk over dx. Okay? I impose that this functional must be minimum. Okay? We also argued that rigid motion is not changing the shape of the body, and rigid motion is not changing deformation energy. So you should understand this. In a generic field theory, the unknown is the field key. We write a functional which has to be minimized, and in general this functional may depend on F. Okay? But we are thinking to use this model for describing the deformation of a body. So we know this is what is called an assumption needed for adapting the general mathematical model to a specific application. We want to say that when this body undergoes a rigid motion, or when a small part of this body undergoes a rigid motion, there is no change of its deformation energy. So instead of imposing that it depends on F, we introduce green tensor. Okay? And we say that the deformation energy total is this functional. Okay? Now, I told you that I will show in some of the next lectures how Lagrange Piola proceeded now. They calculated the first variation of this functional and they found partial differential equations, which are necessary conditions for a configuration to be a minimum. Okay? So they tried to solve this problem with analytical methods. However, nowadays we can solve this problem with numerical methods. And tomorrow you will see how COMSOL can solve exactly this problem. There is an already available package. You give the right instructions to COMSOL, And COMSOL solves for you this problem. But you must understand what it is doing. Okay? Now, let's move a small step. Can a computer determine the value of a field? Think about this. K is a set of 3 functions depending on 3 real variables. How many numbers do you need for characterizing a field? How many pairs of numbers do you need for characterizing a field? You need infinite, but a very bad infinite, a continuum infinite. Even not the cardinality of this infinity is not the cardinality of natural numbers. It is a continuum cardinality. So a computer cannot calculate this field. We are obliged to invent an approximation method. Otherwise, the calculations cannot be done. So what can we do? I consider ki of x1, x2, and x3. Okay? I start decomposing this in k11 x1, k12 x2, k13 x3. Okay? Is every function the product of 3 functions? Is every function of 3 variables the product of 3 functions of 1 variable? No. Okay, so I'm not happy. I must improve it. So k1 of x, I write summation over alpha. Okay, and I write alpha here as another index. So I write this function of 3 variables as sum of functions which are decomposed as products of functions of 1 variable. Okay? Then I ask myself, if I have 1 function of 1 variable, can I approximate this function with a polynomial? We already discussed Weierstrass theorem. Okay, and we have already understood that applying Weierstrass theorem as it is may be very difficult. So what we will do? We will decompose our interval, the domain of our function, into a large number of sub-intervals. Okay, now what we are doing? We will repeat this procedure for x1, x2, and x3. So what we are building, the Cartesian products of 3 intervals, which is a cube or a parallelepiped. Actually, finite elements are decomposing the domain into tetraedra. But okay, this is a technical aspect of the question. Okay? By the way, soon in our discussion will play a relevant role the concept, for instance, of Lagrange. polynomials. Lagrange gave his contribution also to this part of our theory. So, which is the idea? In every sub-interval, I define a polynomial. Of course, if I define a polynomial like that here, and then a polynomial like that there, this is very bad. Because we want to approximate a regular function, and we are not introducing some artificial jumps simply because we want to approximate our function. Okay, so what we must do, we must glue the polynomial in one interval with the polynomial in the other interval. Okay? Now, the reasoning which you must follow, of course, this is not a very serious, rigorous discussion. Again, this is a very intuitive discussion which we will try to formalize a little bit better later. I have a functional which depends on the gradient of the unknown field. So, do I need to approximate in a good way the second derivative of the field? This is not important. What I need to approximate very well is the first derivative of my field. Okay, so instead of using this decomposition here, what is most likely good to do is to approximate every partial derivative like that. Of course, you must be careful because you have Schwarz's theorem, so the cross derivatives has to be equal. So the process of building a piecewise approximation of your unknown function is not easy, and there are very tricky aspects of these constructions which has to be taken into account. Okay, so we need to carefully build the family of functions which are used to approximate our fields, those which are conceived for minimizing the solution of this function. Okay? So we will dedicate some lectures on this aspect of the story. However, I ask you to believe me for the moment when I tell you that we can choose a partition of the body into a finite number of subsets. So we have C star, which can as union over an index beta belonging to 0, 1 to capital N being very big, of C beta. Okay? The numerical method we are using will depend essentially on this numbering. There are people who spend their life in building automatically the correspondence between n natural numbers and the elements of a partition to speed up the numerical process. Okay? There is no reason one could also invent 3 sets of indices, and one could label each of these elements with the index 1, the index 2 and the index 3 varying in the set of natural numbers, in order to remember the fact that you have an object in a three-dimensional space. I try to explain you this with a drawing in 2 dimensions. If I take this square and I partition it in this way, okay, what can I do? 1, 2, 3, 4, 5, 6, 7, 8, and so on. Look how bad is this. You must write in your computer that the cube 1 is close to cube 6, 7, and 2. So your geometry is lost in your numbering. If instead you label in this way, this is 1, this is 1, 2, 1, 3, 1, 2, 1, 2, 2. I remember always a colleague of mine who was kicked out in the exam of linear algebra by our professor, other times. It could happen that you never pass an exam, repeating it 20 times. And I think that this was a good method. But anyway, he said, not 1, 1, he said 11. Then he 12. The professor said, please, explain me what you are doing. He could not say that 1 and 1 were the labels of 1 row and 1 column. And he was kicked out. The professor did not accept to continue the exam on this basis. And he went away crying, I don't know what I said wrong. Okay, which is the fundamental reason for which you have troubles. Okay? Why this labeling is very good? This labeling is very good because what is close to the element ij? I minus 1 j. J plus 1 I. So the rule of being close is very easy. Change the index of a value 1 and you are close to the other. Instead, with the other numbering, it is rather difficult to explain what it means that 2 elements of the partition are close. Okay? So, tomorrow you will start seeing this. The initial move is to build a discretization mesh. A discretization mesh is the choice of a partition of your region, C star, into a family of small subsets. Okay, this is the first. Second step, I need to specify the class of piecewise polynomial functions which I want to use for approximating my solution. So what I want? Which are the dreams? The dreams are the following. I want a placement key such that it is non-vanishing in one element of my partition. Okay. Maybe in the surrounding elements it quickly goes to 0. Okay. And then it is 0 everywhere else. And I want to write my key as a sum of all these functions. So I have a localized function. These are called test functions. So you have a function which is a polynomial in this box and probably also in the box around it. Then it goes to 0 and it is vanishing outside. Okay? So we can call, if I've introduced C beta, the generic element of this partition, I can call key C beta a function of x and a certain number of parameters, which we can call P1 beta, P2 beta, Pn beta. If you are particularly, if you have some needs, you can do a mesh with varying number of parameters in every element of your partition. So in general, n beta. Here you may need 20 parameters, and here you may need 10 parameters. Or here you may need 5 parameters. Why limiting ourselves? Okay? And then, so remark that this is a given function of x. Okay? So this is a polynomial or set of sum of polynomials. I mean, this is a polynomial, okay, in general. And you have that when x minus x beta, this is a point chosen inside your C beta. There are several ways for choosing it. When x minus x beta is greater than a certain small number eta, this function is 0. Okay, so what we are doing? Think slowly, there is nothing difficult. I'm not giving you details, I'm giving you the general ideas. What we are doing? We are first partitioning C star. Okay, so representing C star as union of some fundamental subset. They can be tetrahedra, they can be cubes, they can have every shape which may be useful. But in general, they are small. Okay, so their diameter is small. The diameter can be varying in different parts, but you have an upper bound of diameters. Okay? Then, in each C beta, you define suitably a polynomial. Okay? This polynomial is assumed to be cut outside, so it is necessarily a piecewise polynomial. So you have a function which is a polynomial inside, and it goes to 0 outside. The only problem is, how sharp is the discontinuity? You can choose a polynomial which on the boundary of C beta has a non-vanishing value, bad, and then impose it is 0 outside. You want sufficient regularity because you need to calculate the gradient of this. So you may impose that this function and its first derivative is 0 on the boundary of the C beta block, okay, and outside you impose it is 0. So in this way, the regularity of the sum over beta of these will be the regularity of the matching conditions you have imposed at the boundaries of C beta. Okay? When playing with COMSOL, you can both choose the mesh and the polynomials in a large set of possible choices. So what you can do, you can adapt your integration scheme if you know rather well what you are doing, and if you have understood how difficult is the problem. Okay? Good. So at the end of the story, what you have? You have an approximation of key which depends on a finite number of parameters. So you have x and p. This vector p is the table, the row, which gathers, or the matrix, I mean, it depends how you want to organize it, the set of parameters which you are left free. Now, can I approximate my solution with this family of piecewise polynomial functions? In general, in order to be closer and closer to a given function. Okay, now I have a problem. I must tell the word Sobolev space. So, where are living these minimizing problems? You need functions for which you can calculate a derivative, and for which the integral of WF is finite. Okay? So let's call this set of functions a Sobolev space. Okay. So the minima of these problems belong to this set of functions. Can I approximate each of these functions with an epsilon error with a piecewise polynomial function? This is a terrible problem to be solved. There are many treatises on this. We are talking about density results in Sobolev space. So we need to know which kind of piecewise polynomial functions may approximate a given function in a Sobolev space. Okay, so in order to be somebody who can handle these things, changing the code, you may need to study how a generic function in a Sobolev space can be approximated with piecewise polynomial function. In COMSOL, you get a finite set of choices, which works very well when you have W of F. So it already gives you the right approximating objects. Okay? Now, take this function and you calculate this with dk approximating over dx. So what you are doing? You take your energy functional and you plug in your piecewise polynomial approximating function. Now, in this moment, you understand why I must be very careful. If I was lazy and I said, look, this function I approximate with step functions like that, and then I blindly calculate the derivative is 0. And this software cannot tell you anything. Because all variations are here in this jump. Okay? So one has to be, you understand that in this process, the matching conditions for getting a good approximation of your solution in the passage from one finite element to the other finite element, it is essential. Okay? Okay. I repeat that if in the energy first gradients are appearing, the codes available in commercial programs are working very well. As in my career, I wanted to study an energy in which here you had second derivatives. You understand that my life became rather difficult. Okay, so we needed to invent tricks for getting numerical codes which were faithful, which were producing results which are reliable. Okay, but maybe we will talk about this later. Okay, so I want to prepare your training of tomorrow. Tomorrow you should come with portable computers. Okay? Now, what we have done? We have introduced a function of n variables. Because P are a finite number of parameters, we have built in this P in this functional. At the end, this becomes U of P. Right? So, we have transformed a variational problem in infinite dimensions into a variational problem which is finite dimensional. The unknowns are not anymore a field or a set of fields, but a finite number of real parameters. This process is called discretization. We have made discrete a continuous problem. Okay? How good is our approximation? It depends on all mathematics which we could develop. How close we are going? It depends on the spaces, functional spaces, which we have introduced. Okay? Okay, so now let's move another step. I minimize this. And this is another long story in the algorithm used by COMSOL. So let us try to justify now the reason for which I wanted to talk now in the previous lectures about Lagrange multipliers. I want that this part of the boundary and this part of the boundary have a fixed placement. So I will not maximize u of p for every variation of p. I want to maximize u of p under the constraint that all c betas which are here have on this boundary a given placement. Okay, so I will write f1 of p equals 0, fk of p equals 0. I will write a certain number of kinematic conditions which impose to my approximating solution that the placement here and the placement there are the given ones. So you understand that these constraints are essential for the nature of our problem. Because this body is deformed because of these conditions. Okay? So now, what I need to describe is the solution of a problem in Rn, because P belongs to Rn, with a set of k constraints. Okay, now just for giving you an idea, we needed to solve a problem for a deformation of a metamaterial. This problem involved something like capital N equal to 3 millions. And K was something like 2,000. So we needed to use a code in which the degrees of freedom were of the order of millions and the imposed constraint was of the order of thousands. This is a complex computational problem. It is a complex computational problem which has to be solved with very tricky algorithms. Okay. Now, let us try to go ahead in finding some good sense reasonings in the choice of the number of degrees of freedom, which is in our hands. So, for instance, imagine, do you know what is a rivet? In airplanes, but also in metallic structures, you have one metallic part with a hole, another metallic part, and here you have a kind of nail, which is a cylinder which goes in. It has one head on one side. In the other side, you must hammer the other head to close, to seal. So this is a rivet. It is called a rivet. The technology of bridge building depended for many centuries on human capacity of building reliable rivets. Navier tried to develop a French technology for building metallic bridges. In Britain, they were ahead, so he went to Britain to copy what they were doing, and everything was, the bottleneck was, if I pull this moves here and this moves there, this moves here and this moves there, which are the deformation induced on the rivet? Are these imposed displacements small enough so that the rivet can stay there 50 years before you need to replace it? Where are the rivets which are broken first, so that I can go there and replace them? So the state of deformation around a rivet is crucial in modern technological application. Now, I have a piece of metal with a hole. This is blocked, this is displaced, and it goes there. I want to know the equilibrium shape of this body. Let us start with the empty hole. Then we will need to place inside the rivet and to study the complex interaction between the rivet, the surface of the rivet, and the surface of the hole, which is another nightmare. But let us start to consider this. Okay? Do you think that this mesh is good? This mesh is not refined enough to describe what happens around the hole. So maybe I'm trying to explain you why we may need a mesh having different elements of the partition of different sizes. Maybe it is better if we do this way. So we built a mesh with varying size. And maybe here it is better if we use a polynomial of higher order in order to represent better the deformation state of your body there where we expect bigger deformations. Of course, which is the attitude of precise people? You know, you should be very worried by precise people. Precise people decide, I want to be precise. Okay? So I include many degrees of freedom, many elements. My mesh has to be very refined. What you get? N is big, either your code is not converging because it is not capable to solve the problem, or you need too much time. Now you must be careful, I tell you, with Diablo II, you know, we bought a computer which is a suggestion of my son. He's using this kind of computers for doing fly simulators, you know, these games with a lot of graphics. And so he was exploiting a computer which was very quick in doing calculations. We adapted, actually, we mounted in a different way this kind of computer, and we got a computer which is rather powerful. We paid something like 20,000 euros for it. Okay. This computer has a big capacity of making calculations. So in 2 weeks, you can calculate the equilibrium of a body with 20 million finite elements. Okay? Are we sure that there is not an error propagating in the code, so that after 20 days the result is reliable? Are we sure that in 20 days you don't have a peak of electricity so that the computer is stopped 1 second, it doesn't, and then it continues doing the calculations, and at the end the result is not at all reliable? What I want to tell you is that we must solve an optimization problem. We must be precise, but not so precise. Too precise means incapable to do anything. There is an Italian thought which is very important. The better is enemy of the good. Be afraid of people telling you, yes, but it can be done better. It means that he wants to block you. Okay? You must choose the dimension of the approximating space of piecewise polynomial functions with a criterion which is very clear. It has to be rich enough to describe the phenomena you have in mind, and it has to be poor enough to be computable. If you do something extremely precise, at the end of the story you will not get any answer. If instead you manage to choose the right compromise between the computing time and the quality of the prediction, then you get a functioning tool. Now, what is very nice and beautiful in COMSOL is that it was the first software which allows you to drive your choices, to decide what you want to do. So it allows you to choose a refined mesh here, a less refined mesh there. Do you know that you want a Lagrange polynomial of 4th order because you have a reason for expecting that you need better gluing of derivatives? It allows you to do it automatically. You click on it and you get it. So the fundamental message is this. You need to know the theory. Now it is worth that you know the theory, even if you don't want to become a coder. Because this tool allows you to enter in the code and to make important choices which may change the result of your simulation. Okay, so this is an experiment which I will try to do with you. I hope that what I said to you is enough for allowing you tomorrow to have a good experience with COMSOL, a first good experience with COMSOL. Okay, so try to come here with the right state of mind. Okay? Okay, thanks.